Okay, this is the first video on oxidation reduction reactions, which is the main topic of 4B and the third important class of reaction in this chapter. This is a pretty important subject, and it actually kind of spans both practical, meaning being able to solve problems like balance this equation and things like that, as well as philosophical and kind of some of the deeper understandings of chemistry. And basically it gets back to that story at the very first video where I said it's all about the electrons. And so I think I will be able to touch on this finally a bit here. But I'm gonna wait for the end. Probably the last video we'll talk about some of the theory behind this as it pertains to oxidation reduction. So I'm going to start kind of just with the basics. So oxidation reduction reactions are commonly known as redox, and the read stands for reduction, and the ox stands for oxidation. So redox reactions are reactions that the short way of saying is that it's reactions that involve a transfer of electrons or a significant change in the way electrons are shared between the reactants and the products in a redox reaction. And I'm actually going to just throw one very simple chemical reaction on the board here, which I will use at the beginning here, which is essentially hydrogen reacting with oxygen to form water. And we have to balance this, so I'm going to put a 2 here and a 2 here. Okay, this is essentially burning hydrogen. This is what happened in the Hindenburg. Hydrogen, of course, is very, very flammable gas, and it burns rapidly with oxygen. So in this reaction, oxygen acts as what's called the oxidizing agent. That's how it got its name. And essentially what that means is that the oxygen molecule, and I'm actually, instead of drawing the bonds, I'm actually going to show the electrons here. So an oxygen molecule shares two sets of electrons, two pairs of electrons with its other oxygen. And of course, oxygen has 1, 2, 3, 4, 1, 2, 3, 4. So each oxygen comes to the table with 6 electrons. Okay, you can count them there. There's 6 there. If you look in the periodic table, oxygen has 6 electrons in its outer shell. I still haven't described that to you yet, but if you look at in the periodic table, in the second row, oxygen is 1, 2, 3, 4, 5, 6 into that row. And so that's what I mean by it has 6 electrons in its outer shell. If you remember, it has actually 2 additional electrons in the first row, 1, 2, but those don't count. Those are non-reactive electrons. So oxygen has 6 in its outer shell. And that's what I've kind of drawn here like this. Hydrogen each has 1 electron. And so a hydrogen gas molecule, each of the hydrogens bring 1 electron to the table, essentially filling that first row, which I will get to in the last video, I promise. So anyway, this is what the molecules look like. Now, oxygen, the oxygen molecule, it turns out, is, from an energy standpoint, very much would rather take electrons from some other source so that each oxygen has 8. And this is so that oxygen could fill that row that it lives on, adding on 1 extra electron to get to the end where neon is. This is very analogous to what when we were talking about chloride. Chlorine has 7 electrons there. 1 more would take it to what its nearest noble gas looks like there at the end, which is actually, sorry, argon. I said neon, argon, in chlorine's case. And so that's why chlorine likes to grab 1 other electron, like in ionic bonding. It would grab it from sodium, for example, in making NaCl either as a solid or as dissolved in a liquid. Similarly, oxygen likes to grab 2 more oxygens so that it can get up to where its nearest noble gas is, in this case neon. Okay, so oxygen is an oxidizing agent because it wants other electrons. It wants to grab electrons. Hydrogen turns out to be just the opposite of an oxidizing agent. It is a reducing agent because it is okay with getting rid of its extra electrons. So these electrons that it has, that is closely controlling, it's pretty much happy. I've got to roll another one in here because there's two of them, but I'm going to throw another hydrogen there. Both of these hydrogen molecules are happy to kind of donate its pair of each of the pair of electrons to oxygen as part of this oxidation reduction process. So what happens in this case is we end up with water, which we've drawn several times, but I'm going to draw it like this now. There's water, okay, and I got to draw another one. Okay, so there's two waters, two hydrogens. So what happens on the left, we add together and we get on the right. And if you actually add up the electrons that I have here, it turns out we have a balanced number of electrons. Each of these O's has 6, but each of these pairs goes to complete. So this pair, I wonder if I can possibly draw this. I don't know if I can. But this pair is going to go here, and this pair is going to go here. So that each oxygen is going to end up with essentially 8 electrons around it. And the hydrogens essentially are connected to the oxygen, but they really don't have the electrons anymore. They've been shifted to be closer to the oxygen. So the water molecule kind of looks like this, where oxygen is happy, it has all 8 electrons. And hydrogen was happy to give them up, the ones that it had that it was sharing. And so the two water molecules look something like this. So in the process, hydrogen acted as the reducing agent, and oxygen acted as the oxidizing agent, and both atoms got what they wanted from an energy perspective. They became more stable from an energy perspective, having the electrons oriented like this, as opposed to when they were oriented like on the left. Okay. So oxygen is, in fact, the whole redox, again, was named because oxidation was a process involving oxygen. And oxygen, turns out, likes to oxidize all sorts of things. I'm showing the simple case here of hydrogen, but another, I'm going to now erase the picture. Another common place where this comes about, and in fact, really a very important subclass of redox reactions, has to do with the oxidation and the reduction of metals. So let's take another reaction where you have zinc. Now zinc metal, meaning it's neutral, it's not charged, it's not an ion, it's not a cation here. It's zinc with all the electrons that a zinc atom is supposed to have. Reacting with oxygen, let's say in a furnace, because if it was just at room temperature, zinc and oxygen could react, but it would produce a zinc oxide. But at room temperature, this might happen over the course of years. So think they have you have a zinc garbage can or something like that, and over time it eventually gets kind of rusty, kind of crappy looking. That's essentially zinc reacting slowly in the air with the oxygen to produce this oxide. Now in a furnace, though, if you heated this thing up, it would oxidize rapidly. It would take a couple of minutes, and the zinc would become oxide in no time. Okay, so in this reaction, the way I've written it, oxygen, of course, is the oxidizing agent. We can kind of examine this oxide a bit to show that in the same sort of way, like in water, the oxygen atoms are really grabbing all of those electrons so that it has 8 around it, and zinc is happy to essentially give up the 2 electrons. Okay. Now, if you remember in our first chapter, in chapter 2, when we were talking about naming of compounds, zinc was one that we actually looked at that commonly becomes a +2 cation, meaning it's generally speaking happy to give up 2 electrons to the cause, whatever that cause happens to be. I think we discussed this in terms of maybe some of the ionic reactions or something like that. But zinc is actually one of these metals that prefers to be in the +2 state. And when I get in the last video, I'll show you why that is. And again, in that earlier video, we kind of had to memorize this a bit, like, well, silver wants to be +1, and iron is either +2 or +3, and you know, etc. And there is a method to the madness there, and it's actually a very important subject to talk about. But in that discussion, zinc likes to be +2. So in this world, oxygen is the oxidizer. Zinc is essentially what is being oxidized. Again, in everyday terms, that kind of makes sense, is that when you think about iron or any metal being oxidized, being rusted, it's reacting with oxygen to form an oxide. Okay, so zinc is being oxidized. Now the flip of this, of course, is that zinc is actually the reducing agent of oxygen. So zinc, in this case, reduces oxygen. So this is, you know, redox, when you actually look at redox reactions, there's always an oxidizer and always a reducer, meaning essentially one is gaining electrons, the oxidizer, and one is losing electrons, the reducer. And it always works in pairs like that. You never have oxidation without reduction. Okay. All right. I think that's where I want to end this one. I'm going to pick back up on the next video, just kind of carrying on this subject. In fact, I'll leave the board just like this.